Now that we've learned about a few different prediction models, we will learn how to evaluate a model's performance. Evaluation is one of the most important, if not the most important parts of predictive analysis. How do we determine which model is better than another for a certain job? The answer is evaluation. We'll examine 4 evaluation metrics in this module: accuracy, sensitivity, specificity, and receiver operating characteristics curves. To calculate our metrics, we need to create something called a confusion matrix. This is a simple 2x2 table which plots the predicted against the actual values predicted by a machine learning algorithm. This table is critical for evaluating a machine learning model. Now, here we can see an example of a confusion matrix. Pretend we are evaluating a medical test for a disease, which can give a positive or negative result. The model will attempt to make predictions about whether the test will be positive or negative. However, not all of those predictions will be accurate. This table will capture all possible scenarios. The top labels of the confusion matrix represents whether a patient is actually positive or negative for a disease. The labels on the left of the confusion matrix represent whether a patient is predicted to be positive or negative for a disease. In the top left, these are the values that the model predicted to be positive and that were actually positive in the data. We refer to these as true positives. In the bottom right, these are values that the model predicted to be negative and that were actually negative in the data. We refer to these as true negatives. In the top right, these are values that the model predicted to be positive that were actually negative. We refer to these as false positives. Finally, in the bottom left, these are values that the model predicted to be negative that were actually positive. We refer to these as false negatives. Now, that was quite a bit of information. I recommend you rewatch this section of the video again if you are still feeling uncertain about these concepts. Understanding evaluation is critical for predictive analysis. So, let's look at the previous concept with an example. Say you're trying to predict whether patients actually have a disease using a machine learning model. Say 100 people are correctly predicted to have a disease. How would you fill in the table? This would mean that we have 100 true negatives. One important note: negative and positive do not have any specific connotations in machine learning. Positive simply means that the result we're looking for is there. In this case, that means we have detected an absence of disease. Negative simply means that the result we're looking for is not there. In this case, that means we do not detect an absence of disease. Let's continue. Say 10 people are incorrectly predicted to have the disease. How would you fill in the table? This means that 10 people have false positive results. Let's say 50 people are correctly predicted to not have the disease. How would you fill the table? This means 50 people have true positive results. Finally, say 5 people are incorrectly predicted to have the disease. How would you fill in the table? This means 5 people have false negative results. Now that we understand what a confusion matrix is, we can begin to learn about specific metrics. The first is accuracy. This simply measures how often your model makes the correct prediction. Accuracy is your sum of the correct predictions, true positive and true negative, divided by your total, which would be all 4 metrics we covered in earlier slides. In the previous example, that would be 91%. Our next measure is sensitivity. Sensitivity tells us how often does the model correctly predict a positive result when there is actually a positive result. Sensitivity can be calculated by taking the number of correct positive predictions, true positive, divided by the sum of the correct positive predictions, true positive, and the incorrect predictions, which are actually positive, false negatives. In our example, the sensitivity is 0.91. Sensitivity ranges from 0 to 1. The closer it is to 1, the better the model is. Our next measure is specificity. Specificity tells us how often does the model correctly predict a negative result when there is actually a negative result. Specificity can be calculated by taking the number of correct negative predictions, the true negatives, divided by the sum of the correct negative predictions, true negatives, and the incorrect predictions, which were actually negative, false positives. In our example, the specificity is 0.91. Specificity ranges from 0 to 1. The closer it is to 1, the better the model is. Our last metrics we will be looking at are receiver operating characteristic curves, or ROC curves. This is a visual way to evaluate a model performance taking into account both sensitivity and specificity. The y-axis of the curve is sensitivity, and the x-axis is 1 minus specificity. The ROC curve allows us to get a picture of overall model performance. The closer that an ROC curve is to the top left corner of a graph, the better its overall prediction performance. You may have noticed the dashed line in the image. This represents the equivalent of the model if it was only as good as flipping a coin or 50-50 guessing. Anything above the dashed line is better than random chance. Anything below the dashed line is worse than random chance. So, since ROC curves are visual, how can we compare two different ROC curves against each other? We can use a measure called area under the curve. By measuring the area under an ROC curve, we can get a quantitative measure of ROC. The higher an AUC value is, the better the model performs. AUC values range from 0 to 1. For reference, the dashed line in the middle has an AUC value of 0.5, representing random guessing. Any model with an AUC value of greater than 0.5 indicates that the model is better than random guessing. Any model with an AUC value of less than 0.5 indicates that the model is worse than random guessing. I would like to end the module and take a moment to thank the following organizations for their support. These modules would not be possible without their support. Finally, are you interested further in health analytics or digital medicine? Consider a graduate degree from the University of North Carolina, Carolina Health Informatics Program. Thank you.